So in order to program computers, it's going to help to have a understanding of how they operate on a fundamental level. And that's going to include an understanding of how number systems work. And so we're going to try to kind of dive into that a little bit today. It's important to understand that almost all the computers that you encounter today, whether they're in your microwave or your automobile or a vending machine or your laptop or tablet or smartphone, they're all what we call binary machines. And that means that they operate on ones and zeros. And you might ask why? Why binary numbers? Why this weird set of numbers in which we only have ones and zeros? Why not just regular numbers that we're used to using on a regular basis that humans use all the time? Surely we use the numbers we use for good reasons. And the answer to that question can be explained by simplicity. Ones and zeros can be represented by a simple switch that's either on or off. Electricity is flowing or electricity is not flowing. We've got electrons or we don't have electrons. Now, of course, we could make switches that have 10 different positions, but those switches are going to be much more complex. And so we get a degree of simplicity out of these simple switches. And it turns out that we don't need anything more complex than simple switches in order to get computers to do everything that they can do. And we're going to be exploring that in this video and in some subsequent sections in the course. So first, I want to give you a sense of the scale of what we're talking about when we talk about these switches inside of the computer that are turning on and off to represent ones and zeros. And so I've got a couple of circles here. This outer circle represents a diameter of 10 meters. And within that, we have some images to give you a relative sense of the size of this. So, you know, an elephant, a giraffe, a family of people, a shopping cart. On a smaller scale, we can see things like chairs and cats and laptops. And so each time we advance here, we're going to zoom in by a factor of 10. So we're going to blow things up 10 times larger. So, and we'll be looking at things that are 10 times smaller. So 10 times down from the scale of things like people and elephants are things like chairs and cats and laptops. And 10 times smaller than that, we see things like pennies and peanuts and field mice. And 10 times smaller than that, we've got sunflower seeds, and we can see ants. And if we zoom in on ants, we can see things like grains of sand, and something the width of a human hair becomes a sizable object. A plankton becomes visible, but the smallest thing visible to a naked eye is somewhere around the width of a human hair. And if we keep zooming in 10 times smaller, we can start to see large single-celled organisms, and 10 times smaller than that, red blood cells and bacteria, and 10 times smaller than that, large viruses and smaller viruses like the HIV virus. And this is where we start to run into things that are too small to see with an optical microscope. And if we keep zooming in 10 times smaller than that, we get into the realm of where these switches inside of the computer actually exist. And what they are actually transistors. And a transistor is a type of switch in which we can control the flow of electricity through it by controlling whether or not electricity or electrons are going to what's called a gate. So if we allow electrons to go to this gate, this will allow electricity to flow through the transistor, thus turning the switch on, making it a 1 perhaps, or we can restrict the flow of electrons to the gate and restrict the flow of electrons through the transistor, thus turning the switch off, maybe making that a 0. And these things are significantly larger, but on the scale of the width of a DNA molecule at this point. And if we keep zooming in, we can start to see things like glucose molecules and water molecules. And this is the realm at which an electron microscope starts to run out of its power to resolve images. And below this, we have things like electrons. And at this stage, at this point, things are starting to get fuzzy, not just because we can't see them, but because they actually are fuzzy. They're distributed probabilistically throughout space. And if we keep zooming down 10 times smaller than an atom, and 10 times smaller than that, and 10 times smaller than that, and 10 times smaller than that. Somewhere down here is where we start to run into the constituents of atoms, the protons and neutrons that make up the nucleus, and the electrons that orbit the atom. And these are the electrons that will flow through those transistor switches or be blocked from flowing through those transistor switches that represent the ones and the zeros in the computer. And so we're going to zoom back out really quickly, and just to get a sense of the scale here. 10 times larger and 10 times larger, and there's atoms and then molecules and then DNA. And here's where our transistors are, something larger than a width of a DNA molecule, but still smaller, significantly smaller than viruses, and much smaller than red blood cells, and incredibly much smaller than peanuts and cats and laptops. And so we're back here in the realm of familiar objects, objects that we can look around and see on a regular basis. And I'm going to zoom in one more time, and then we're going to zoom back out kind of through a different path and see how this applies to computers. So if we zoom back down in to these transistors that are millions of times smaller than the head of an ant and tens of thousands of times smaller than a red blood cell, just larger than the width of a DNA molecule. And now we're going to zoom back out. And what we can do with these tiny, tiny switches, these transistors, is package them and reproduce them reliably and efficiently and inexpensively. And then with these switches, we can build simple circuits. We can build simple circuits to represent simple logical operations, like an AND operation, which compares two inputs to determine whether or not they're both on, or an OR circuit, which compares two inputs to determine whether one or the other is on, or a NOT circuit, which determines if another circuit is on or off. And we can use the outputs of these to control other circuits. And so we can package these simple circuits into what we call logic gates. And from these logic gates, we can compose the circuitry of a computer. So what we have here is an example of a simple one-bit adder that adds two one-bit binary numbers in the same way that you would add two one-digit numbers in the system that you're used to using. And we can pack these simple circuits for adding binary numbers into a space smaller than a bacteria. And when we package these things, we can put them together and make more complex circuits that can add 8-bit or 16-bit or 32-bit binary numbers. And we can make circuits that add binary numbers, and circuits that subtract, and circuits that multiply, and circuits that divide, and circuits that compare. And we can pack all of these into a space that's smaller than a paramecium. And these set of circuits make up the logical operations of the computer, and they reside in a particular component called an ALU, an arithmetic logic unit. And we can etch these circuits into silicon, which is really just the primary component of sand. So we make these computers, these circuits, out of sand, which is abundant and cheap. And when you're looking at this section here that's about 1 millimeter across, you're looking at millions of transistors, smaller than the head of an ant. And if we keep zooming out, we can build all the circuitry that we need for a computer to do all the fundamental things that a computer needs to be able to do. And we can pack this inside of the CPU, which sits on the motherboard of your laptop, all so that you can play video games and check your email and compose music and watch this video. And so maybe now we understand how the computers operate using only ones and zeros with these transistor switches. But we still maybe don't understand how ones and zeros allow the computer to do all the things that it can do, because the computer can do math like you and I can do math. I can pull up a calculator application in the computer, and I can do math like 9 times 9, and it will tell me 81, and 9s and 8s are not ones and zeros. And the reality here is that binary numbers are completely equivalent to decimal numbers. And it'll help if we understand how decimal numbers work. And decimal is just the name for the numbering system that you've been using your whole life. And I've got an example here of several decimal numbers, and you're very familiar with this already. This first number we call 1. This one we call 10. This one we call 102. And of course, this is in English. In other languages, we have different words for these numbers. This is 1024. And this is, well, this is a very large number. It will help if we break it up into groups of 3, and then we know that this is our hundreds and our thousands and our millions and our billions and our trillions and quadrillions and quintillions. So 102 quintillion, 456 quadrillion, 789 trillion, 98 billion, 765 million, 432,123. So it takes a little bit of work, but we're very fluent in this, and it's because we've been working with numbers like this for a long time. And you know how to do basic mathematical operations. You can add, subtract, multiply, divide numbers like this. And you've been doing it for so long, and you learned it at such a young age. And in some ways, it's like learning to ride a bicycle. There was a time, if now you maybe know how to ride a bicycle, there was a time in which you didn't, in which it was difficult. And then you've learned, and it's now so obvious and so simple that it's difficult to explain to someone else how to ride a bicycle. You just get on and you pedal and go. And your fluency with this number system is similar because of the amount of experience that you've had with it. And that would be true if you had the same amount of experience with binary. The good news is that binary is much simpler, and you already know how number systems work. So once I explain to you how binary works, or the difference between binary and decimal, it's going to be quite simple for you. So let's just take a quick look at this number, which we almost intuitively know is 1024. It's interesting to note that when you look at this number, there's not 1024 of anything here. It's just 4 symbols. This kind of tall, thin one, this round, fat one, this one that's round on top and flat on the bottom, and so on. Yet it symbolically represents this value, 1024. And the way that it does that is by using these symbols, each of which is associated with a particular value. This tall, thin one is associated with the value 1. This one that's round on top and flat on the bottom is associated with this value, 2, and so on. And then we arrange these symbols in columns, and each of these columns has a value, the rightmost column being the 1s, and then our 10s, and then our 100s, and then our 1000s. And so the way that this symbolically represents 1024 is because it's saying there are 1,000s, 0 hundreds, 2 tens, and 4 ones. And if, of course, you add those up, you get 1024. But this is what 1024 of something looks like. We've got 512 small white squares here and 512 small black squares, which is a total of 1024 squares. And it's fascinating that we can symbolically represent that with such a concise notation using this numbering system that we call decimal. And that's the advantage of numbering systems. And binary has its advantages as well. And that's why we use binary for computers.